Yeah, absolutely. I kind of do my warm-ups. All right, so we have an Atwood Machine problem, ideal string, ideal pulley. There are two approaches. Both approaches require the same first two steps. Step number one, assign a direction of motion. You have to decide what you're going to call positive and what you're going to call negative. And this system can only move to the right, left and right up here, and up and down for mass B. I'm going to go ahead and call anything that moves in the clockwise direction positive. So whether you're using the long way, which I'm going to do now, or the short way, which I'm going to show you in just a bit, you have to start with either of those two. We're also going to draw free body diagrams of both of these masses. There's mass A and there's mass B. What is at least one force acting on mass A? What do you got for me, Mr. Bleeker? Yeah, gravity. What's the direction of the gravitational force? Downward. So we have gravity acting downward. What else, Daniel, is acting? Normal force, and that direction is upwards. And I'm going to be very careful here. This is MA times G, and this is force normal acting on block A. Although, as we'll find out, there's no normal force acting on block B, so I don't have to worry about that. Any other forces, Alex, acting on block A? Well, if we assume that there's no friction between these surfaces, somehow DuPont has made something that is so frictionless, even better than Teflon. What do we got? There is going to be a force on A from B, but it goes through the string. What do we call forces through strings? Tension. So I'm going to go ahead and add F sub T as a force acting to the right. And what are some forces acting on block B? Joe, what's one of them? Gravity. I'm going to call that MBG in the downward direction. Another one, Joe, acting on B? Tension. FT is going up. I'm now going to write dynamics equations. Those are two completed free body diagrams for both individual objects in the system. There are two of them. Let's go ahead and write our dynamics equations. Is the sum of the forces in the y direction equal to 0, Randy? For block A, the sum of the forces in the y direction. They are. Your evidence for that is? It's not moving, it's not accelerated. So we can say then that the normal force minus MAG is equal to 0. And how about the sum of the forces in the x direction? Are they equal to 0? What do you think, Mitch, in this problem? For block A, when we add up the forces in the x direction, are they equal to 0? No, they're not. There's only one force acting on block A, and it's moving it to the right in the positive direction. So I can say then that the tension is equal to the net force. There is only one force, it's F sub T, and anytime we have a leftover force, we call it F net. Remember that in dynamics, all that matters is what's left over. Imagine that I walk over here and I drop, $50, Jen, right in the table in front of you. Or, in a different scenario, I put $100 in the table and then I take $50 away. At the end of the day, all that matters to you is that you walk away with $50. And in a slightly more impressive show, I could bring $10,000 over and remove $9,950. And although the stacks of 20s would look really nice, at the end of the day, you're just left with $50. And that's the only thing that really affects you. And you need to think of dynamics in the same way. The only thing that really matters at the end of the day is how much force is left over. It doesn't matter how you got there. It doesn't matter how you got that leftover force. The magnitude of that leftover force is all that matters. Let's take a look over here at mass B. Adam, can I say that the sum of the forces in the y direction for mass B is equal to 0? So mass B is not going to move. We definitely have an upwards force and a downwards force, but if A is going to move to the right, and these are tethered together through a string that's connecting the both of them, we can say that there should be a leftover force. And if we're not sure, then we assume that there is a leftover force, and our dynamics equations will eventually show us that the acceleration is 0 if there isn't. So if you're not sure, you can say, hey, let's answer the question no, and therefore the right-hand side of the equal sign will be F net, and my equation should look like this. What's positive? gravity is positive, mbg, and we have to subtract the force of tension. And the reason is we unified our direction here with saying that anything in the clockwise direction was going to be positive. So that means then that going downwards is positive and up is negative. The other thing that we see here is that the tension has to have an opposite direction. This is a positive tension. This is a negative tension. So if I hand you one piece of a rope and I pull on it, the forces on the rope are in opposite directions. They have to be. They're under tension. They're getting pulled apart. And so now I have an expression here. This is Ft. I can write the force of tension is equal to m times mass A, m sub A times acceleration. And over here, this becomes mbg minus force of tension is equal to the mass B times the acceleration. Now, this is a classic problem in any physics question where I have multiple unknowns. I have acceleration, which is not known, and force of tension. But they're the same two variables in two different equations. What do we call that in mathematics? Good, a system of equations. There are multiple ways of addressing a system of equations, and one of them is substitution, or the addition and subtraction, or graphical methods. Let's go ahead and substitute. I'm going to take f sub t, which is ma times a, and plug it in right here. So this expression for ft is going to go in right there for ft, and I get mb times g minus ma times a is equal to m sub b times my acceleration. What am I solving for in this case? Acceleration. That's what the question is asked. How do I isolate the variable a? Good. Yeah, we need to add this guy to both sides first, and what you guys are actually doing algebraically is you're grouping, right? You're putting all your like terms on the same side. This becomes mb times g is equal to mb times a plus ma times a. Now I'm going to factor out an a. That becomes mb plus ma. Dan, I think you were just about to say that. Times a is equal to mb times g. Any questions algebraically on how I've arrived here? Now I'm going to isolate the variable a and divide both sides by the total mass in the system, which is mb plus ma. And my expression looks like this. mb times g divided by mb plus ma. And there's my expression for acceleration in terms of those fundamental constants and variables. Xerxes?
How do you know whether to use m times g or m times a when you're substituting for forces?
Okay, anytime, so Newton's second law, and this is Isaac Newton's Principia, one of the biggest ideas to come out of that masterpiece is the fact that leftover forces cause accelerations. And they're proportional to the net force and inversely proportional to the mass. In other words, that's just a really fancy way of saying F net equals ma. So anytime I have an F net, I will substitute ma in for it. That's just another way of doing it. As a matter of fact, once you get good enough at dynamics problems, you'll never even write that. You'll just, as soon as you get a leftover force, you'll set it equal to ma. Yeah, ma. Does that answer your question?
So what exactly do you use
mg is what we use for weight. So anytime we're talking about the gravitational force acting on an object, instead of putting, you could think of it as just another substitution. Instead of just saying Fg, which could be an intermediate step, we always just write it as mg, because that's the way of figuring out the amount of newtons or the amount of force that the Earth is pulling downwards with.
So would you always substitute Ft equals ma is the larger equation almost? Or
You don't have to. You'll get the same expression if you want to make life difficult for yourself. And
you might as well just put it in.
you might as well. Another way of doing it, Jen, is to set Ft equals to ma, and then solve this one for Ft, and set them equal to each other. Yeah.
I remember doing that.
Yep. Okay. Okay, let's stop there for a second, and I want to talk about an alternative way of solving an Atwood's machine problem that we have not yet discussed. And it's going to be a classic example of when I show this to you, you guys are going to say, why didn't you show us that the first time? Because that's a lot easier. And the answer is you can only use this additional method when you're not being asked anything about the internal forces. The internal forces in this case would be the force exchanged through the string, or tension, between A and B. If you're asked nothing about tension, you can shortcut this by simply treating it as a unified system and only looking at the external forces acting on this object. And so now I can really redraw my free body diagram of saying that A is actually connected to B. There's, of course, a string there, but we're going to ignore now the forces in the string. We're only looking at external forces. How much force is trying to pull the entire system down this way in the positive direction, and how much force is trying to pull it in the negative direction? And that's all we care about. And so now I can simply say, well, there's only one, this is my simplified free body diagram, there's only one force trying to accelerate the system in the positive direction, and that is the weight of object B. And to your point earlier, Xerxes, I could write that as W of B or F sub G, but I'm just going to go ahead and skip that step and just say it's mg. It's the weight acting on object B. That's the only thing. The weight of A does not try to accelerate the system to the right in the positive direction. Is everybody comfortable on what I've done? I've really taken the Atwood machine and I've stretched it out. And I'm now imagining that it's moving side to side. And the only thing that's trying to pull it, I guess, in this positive direction is the weight of the Earth's weight vector pulling down on it. And there's nothing trying to move it to the left. There would be if there were friction, but there is no friction in this case. Are there any questions on this simplified free body diagram? Okay, so when I write my dynamics equation now, I need to make some adjustments. And so I'm just going to kind of get rid of this stuff over here so that we can go ahead and do this one more time. And my dynamics equation simply is going to be the leftover force F net is equal to mb times g. There's only one force acting on the entire system if I only look at the external forces and I ignore any of the internal forces. And then therefore I can say, well, the net force is the total mass in the system times acceleration. Notice what just happened right there. I substituted in for F net. I substituted ma, but it was the system-wide mass, the total mass of A and B together. Another way of describing m sub t would be saying that it's the sum of ma plus mb. And so now my expression for acceleration becomes really easy. It's just the weight of object B divided by the total mass in the system, ma plus mb. And if you're paying attention, you'll see that we got the exact same expression for acceleration that we did the long way in about 1/4 of the time.